Welcome back to this tutorial series, and in today's video we're going to be implementing our calculator with our infinity approximator for integrals. If you don't remember, in a previous series we implemented a recursive descent parser for a calculator. It is an extremely powerful tool, and we're now going to implement it with our function like we have been doing in this series. But before we begin, I'm going to give a few more examples of our infinity method. So last time, we're going to pick up exactly where we left off last time. In the last video we went over a bottom value which was negative, but now let's do a bottom value that is positive. So we're going to integrate from 5 to infinity, which should be the approximate value of 0.19. So now we're going to run this. So we needed only 5 iterations because our lower bound is positive, so we only ran once. We got 0.19. 0.25, so as we can see here, we're pretty accurate. And now what we're going to do is we're going to test this at a bottom value of 0. So I change this to 0. We should get 0.785. We needed 5 iterations for this first call, and we needed 23 iterations for the second call in our adaptive composite Simpsons rule, and then we got our approximate integral. So as we can see here, this is an extremely useful tool. And now I'm going to implement this with our calculator. Alright, so now we're going to take our function here, get rid of that, we're going to make a new one. Copy paste, call this calculator, and we're going to redo these parameters. We're going to pass in our parser, our tokens, for our function, and we're going to pass in our inverse parser, our inverse of our tokens. And we're going to change these to a calculator. But before we do that, we need to actually import this. I'm going to simply copy and paste. All the way through, and then our function here, we need to pass in our parser and our tokens. And same thing here, pass in the parser and the tokens. Pass in the inverse parser and then the inverse tokens. Here as well. And then simply, we don't need to do anything else because our adaptive composite Simpsons rule takes care of it by calling composite Simpsons, where composite Simpsons performs the adding variables, replacing them, and deleting them. So we don't need to do anything, we just need to call it and return it. And so now we actually need to find a way of getting our input. And so we're going to say my parser is equal to parser. We're going to make a while loop. So we're going to say while true. Our standard input is going to be from the we're going to get it from the user. We're going to say enter function if standard in equals q or standard in equals quit. We're going to break. Else, we're going to get our tokens from the scanner of our standard in. And I just now noticed I forgot to actually import these. So we're going to first import from scanner, import scanner, from parser, import parser. And these are our created files from our recursive descent parser. So now we get our tokens. The next thing we need to do is create our inverse function from these tokens. Alright, so now since we have our tokens from our function, we need a way to create our inverse function. And we're going to do this by the following. So we're going to have our prepend tokens is equal to scanner of 1 divided by x to the negative second power in parentheses. So this is our prepend here. Excuse me, not negative second power, just squared. So we have our prepend tokens. Then now what we need to do is we need to iterate over our standard input tokens called tokens and see if an ID occurs. We need to take the inverse of that ID. So we're going to make our new inverse tokens to an empty list. We'll say for toke and tokens. We're going to say if toke.token equals ID. Else, what we're going to do is we're going to append. So I'm going to say inverse tokens.append our token. But before we do that, we actually need to import our token class from our scanner. So now, if we have an ID, this means it's an X variable, and we need to take the inverse of that. So now what we're going to do is we're going to say our temp tokens is equal to scanner of 1 divided by X. And then instead of appending this ID, we're simply going to take these temp tokens and insert them at that same index. So inverse tokens is equal to inverse tokens plus temp tokens. And then we need just to continue as normal. And then at the very end, we need to say our inverse tokens is equal to our prepend tokens plus our inverse tokens. So there we have it. We take our inverse tokens, and if we have an ID, we simply get the temp tokens from this, which simply takes the inverse, and we add that, and then at the very end we add our prepend tokens. And we also need to make our parser for our inverse. So we're going to say inverse parser is equal to parser. And then the last thing we need to do is simply just call our infinity. So we're going to say our value is equal to infinity calculator of our my parser, our tokens, our inverse tokens, our inverse parser, and then our tolerance and our A. And then we're going to simply print estimated integral string of value. But before we do that, we actually need to get our tolerance and our bottom value. So here we're going to say tol. Actually, we're going to get our A value. We're going to input, enter lower bound, get our tolerance, and we need to convert these to a float. So we don't want to pass in the string value. So there we have it. Let's actually run this now. Enter in our function, 1 divided by x to the second power. Our lower bound is going to be 1. Tolerance is 1 e to the negative 10. So here we go, we're having an issue here. And so here we are, we're trying to add a variable, we're trying to call the function add variable on a list object. This is because I'm calling or passing in our tokens instead of our parser first. So now I'll just fix that. Let's run this again. 1 divided by x to the second power, 1 to infinity, tolerance of 1 e to the negative 10. So maximum iterations reached. So here we probably have an error somewhere in our inverse tokens. Alright, so after debugging, I found out exactly why our function was failing. And before we begin to that, I'm actually going to adjust our original. So there's no reason simply to create an empty list for our inverse functions and then simply prepend our tokens at the very end. What we can do here is simply assign our prepended tokens to our inverse tokens. That way we start off with these tokens. However, if you remember correctly from our scanner class, at the very end, let's see here, right before we return, we append the $sign tokens. So every time we call scanner, we are appending the $sign tokens. So we actually need to get rid of that. So we're going to say delete inverse tokens, -1, which simply deletes the last entry of our list, and that is for the $sign. And we're going to do that here as well, except instead of inverse tokens, this is going to be our temp tokens. So we delete the last entry from our scanner here, and then we delete the last entry from our temp tokens, assign it, and since we're going through all the tokens of our original function, the last entry is also going to be the $sign. So we need to delete it as well. And then we also need to do is to adjust our prepend. So what we want to do is we want to take this value times the entire function. So we're going to surround the entire function in parentheses to make sure this occurs. Get rid of this line. So we're going to append the token, call this rpar, we'll write parentheses, and then we're going to simply append the $sign token to indicate the end of the input. So now let's run this. 1 divided by x squared, lower bound of 1, this should be an integral value of 1. So there we have it. You did only one iteration, we got our estimated integral to 1. So exactly what we did here was we made our prepended function, then we wanted to surround our entire function in parentheses. So this is what we did here. However, our scanner class appends the $sign token at each call, so we need to delete the last entry, and we need to iterate through our original function, and if we encounter a variable, also known as an ID, we need to insert these tokens, while also deleting the $sign tokens. So then we add it to our inverse, and if we don't reach a variable, we simply just append whatever token it is, and then as we said before, since we're going through all the tokens, we're on the last iteration, we're going to append the $sign token, so we need to delete it, then we need to add our ending right parentheses for our function, and then we need to append our $sign token. So that is how we get around the input, and as you can see, we can even run this again. Let's say for 1 divided by x squared plus 4 on the bottom, lower bound of 0, tolerance of 1 e to the -10, this should be, I think, 0.785. And there we have it. We needed 19 iterations for the first call and 83 iterations for the second call. So there we have it. We have our infinity calculator for integrals implemented with our calculator. So this is an extremely useful tool. Hopefully you guys have learned a lot from this, and stay tuned for future videos.